So what I'm going to do in this first 20 minutes is give a little bit of an overview of the things that you can expect. Well, I don't have to explain too much. That's an advantage because almost everything that I'm going to show will also be elaborated by other people during those next 2 days. Okay. So typically here in Wageningen, when we talk nowadays about G by E or G by E by M, we show this slide. This is a slide that is the first slide. There is some extra echo here. Is that possible to take it out, or is it because of the microphones there? Well, so this slide is one of the first slides in the course for plant breeders and plant scientists on G by E, and let's say it's called data science for plant breeders. In the past it was called statistics for plant breeders. It was not so popular. So it's better, let's say, to adapt yourself a little bit. And what you see, of course, is typically, well, there are individual experiments. These data then are ordered. Well, this is the experimental field that you see, and in this case, there's some imaging done on top of it. Of course, the data are analyzed by mixed models. There are summarizing vectors of genotypic means, blues, together with the standard errors obtained from the mixed model. These go to a second stage in which we're going to look at the G by E. And then finally, when we understand a little bit the patterns in this middle part of the slide, we try to find the genetic basis for some of the phenotypic features that we identified. And then another slide, oh wait, I have to do this. Another slide that typically occurs at the beginning of each of my talks and also in the course is this one in which the basic, well, let's say visualizations of G by E are shown. And yeah, what is genotype by environment interaction? Well, mainly that when you look at the phenotype for a few set of genotypes, for example, there are 3 genotypes here, and they have what we call different ways to translate the environment into the phenotype. This function is called the reaction norm. So these reaction norms, they diverge. And if you think on the horizontal axis, there's something like environmental quality. When you go from left to right, well, the environment improves and the difference between the genotypes increase. And let's say this non-parallelism of the reaction norms is the easiest way to talk about G by E. There are many ways in which you can look at it. You see 2 basic models for it. And I mean, this is the analysis variance model, probably about 1 century old. And there, well, the idea is if you cannot predict what's happening for a particular genotype in a particular trial or environment, you need some additional term, this G by E term. And if you have to do that, well, for many purposes, you're a bit in trouble because if you evaluate your material, you will have to do it in all conditions that are of relevance to you because the relative importance of the genotypes can change depending on the condition. So our effort is to change this thing that has 2 indices in something kind of function in which you have inserted parameters that only depend on the genotype and the environment. Okay, there's another more modern way of doing it, and nowadays, let's say we do almost all of these things with mixed models. Well, then the formulation looks slightly different, and then the question becomes, okay, the genetic information or the genotypic effects that occur in a particular trial or environment, can I say something about how the genetic variances depend on the environment and how the genetic correlations change between pairs of environments? Okay, so the most simple way of doing something about the problem, especially in this simple 2-way analysis of variance model, is to find descriptors on the genotypes and the environments that help you to simplify this G by E term. And for the genotypes, well, that is equivalent to finding nowadays markers, IBD probabilities, trying to group the genotypes in groups that make sense, for example, adaptation groups, or let's say, try to group them in terms of resistance tolerance versus certain dominant stresses. Well, these different ways of characterizing the genotype can be qualitative and quantitative, but I mean, in essence, is nothing else than inserting information on the genotypes in your analysis of variance model. And if you do the same for the environments, it's not so difficult to think that, well, the environments might be grouped on the kind of phenotype they induce. So they can be grouped in terms of their dominant stresses. And well, nowadays we know there's a lot of work on envirotyping, environmental scenarios, adaptation zones, and also during this conference a lot of that will be shown. And of course, we have many people that work on characterization of the environment by using crop growth models. Well, you can have soil and weather information that you can try to insert directly in the statistical model. You can also first try to integrate the environmental information via a crop growth model and then insert in a statistical model. I think these are all ways of hybrid modeling of G by E. Okay, if we rely more strongly on the interpretation of G by E in terms, let's say, of random effects, then our work is to try to find the reasons why certain genotypes behave the same and why certain environments behave the same. And it's not so very different from, let's say, the interpretation I gave just a minute ago in the ANOVA context, but it's more that we try to reduce the complexity of the association patterns, of the correlation patterns, and try to find underlying reasons in terms of genes, QTLs, adaptation, envirotypes, etc. Oh, this is not the right one. So, at the beginning of the course, Data Science for Plant Breeders, the students are trained to interpret a number of those plots in a way that allows them to tell, okay, which genotypes show comparable adaptation across trials, which environments induce similar types of G by E. And those kinds of plots then, in principle, would be a first step in trying to fit decent random mixed models for the G by E structure. Okay, now one element that I think is, well, I mentioned it a number of times already, separability. Separability is not a very well defined mathematical term, but basically what we try to do is, and you can see it here, we try to write the original G by E term, in this case, typically as a product or something that looks like a product. Here's an genotypic sensitivity, environmental characterization, quality. These kinds of descriptions can be obtained by optimizing mathematical criteria, but there are quite a number of ways of doing that. And well, this is a very simple way of trying to get a hold on the G by E. And yeah, the work for the breeder then later is try to understand what these hypothetical environmental characterizations mean. Now, it's easier to understand what you do when you introduce explicit genotypic information. These X's is simply marker information for the genotype I. We have a number of those that are related, let's say, to genes or QTLs. And what we estimate is this beta here, and beta E is just a QTL effect that depends on the environment. There's the index J, which means if you go from one environment to the next, this QTL effect will change. And, well, to a large extent, we try to understand G by E in this way. And actually, one step further, we try to understand whether this QTL expression that depends on the environment, which environmental drivers actually cause that QTL expression to change. Nowadays, with phenotyping platforms and any other way of, let's say, modern phenotyping devices, we could try to measure another trait on the genotypes, and I for the genotype, and this Y, well, it's just a secondary trait as we call it, and we might try to insert that secondary trait in an attempt to explain the G by E for a target trait like yield. Okay, this is when you introduce information obtained on the genotypes. Here's an example for the environments. Well, for the environment, it's relatively simple to imagine because, for example, you use your crop growth model to calculate some kind of stress index, and then Zj would be the value for that stress index in that particular environment, and then you try to estimate the sensitivity to that stress index. And well, you can do that in many ways. This is simply linear, but you can insert various ways of doing that non-linearly. And if this works, you might also go one step further. You might try to understand the sensitivity of the genotype to your constructed stress index in terms of markers. And well, this expression here is nothing else than that you insert a marker profile to predict the genotypic sensitivity. Okay, now a kind of intermezzo. This is not terribly important, but it's necessary to understand the next slide. In mixed modeling and also in penalized regression, rich regression, there's a kind of trick. You can try to insert many predictors, let's say, for the difference between your genotypes. This matrix Z might contain 1 million markers, and these markers have been scored on every genotype. And then you can try to estimate the effect of each of those markers as a contribution to the phenotype for each genotype. And you can make the simple assumption that, well, the effects for all of these markers, all of these QTLs, come from the same normal distribution. If you do it in that way, well, it will take a lot of time to estimate these marker effects. So the trick is, instead of inserting this design matrix, you define a so-called kernel matrix, and the kernel matrix is nothing else than a kind of similarity matrix between the genotypes that condenses all of that marker information. So the total of the marker profiles are used to, in a sense, estimate the similarity between the genotypes. And if in this second definition, in the second formulation, it's a lot easier and faster to fit your mixed models. And if you look at the literature, there are lots of papers that, well, start from this model over here. This is a two-way model, but can be generalized. And then as soon as they start to look at the genetic effects, well, this is a rather unreadable expression, but it doesn't mean anything else than that we try to model the correlations between genotypes and environments and the variances. We try to model them once again in what we call a separable structure. On the one hand, we try to define the relations between genotypes, that is in the A matrices. On the other hand, we have the relations between the environments in the B matrices. And we can insert in these so-called relationship matrices all kinds of information. Of course, it's relatively easy to imagine that you use markers to identify the similarities between the genotypes, and for the environments, well, you could use environmental characterizations. And if you look at the work by Jarquin and co-workers, Gustavo Los Campos, José Crosa, they make a lot of work on finding ways to characterize these environmental relations based on these environmental relationship matrices. Well, in this way is a very flexible way to play around with inserting a lot of information and also integrating different types of information, because you can also use omics data, phenotyping platforms, whatever, to define those relations between different genotypes. And for each effect that you want to define, it can have its own product matrix of genotype times environmental relation. Okay, now a little bit more traditional, because this is, I think, what I just showed is where we are with respect to mixed modeling. What I show here is what people have been doing for 60 years. If you have a number of trials, different locations, years, well, then you have this three-way model. This is typically a mixed model. Most of the genetic terms are random, and well, the environmental main effects are typically fixed. And nowadays, we can extend that also including management effects. Well, you see that this factorial elaboration becomes rather large immediately, so quite a number of these terms probably don't matter that much, but this is a simple way of taking care of both the environment and the management. And large part of the work that I've been involved with over the last years in projects like Invite and Invita, about which you will hear more the coming days, was on trying to find regions or adaptation zones that can be used to explain the G by E, or find environmental scenarios and envirotypes that do the same. And the difference between them is, well, regions are defined on locations, grouping locations, and envirotypes are defined on grouping trials across years and locations. Well, you can make that more complicated, because in the end it's a kind of Lego box. These terms here, GL, GY, G by L by Y, you can try to find environmental descriptors to which the genotypes differ in sensitivity, and that explain part of this random variation. I mean, in a sense, we try to undress the random variation for the G by E in parts that we understand, and mostly when we understand it well, we can insert those things as fixed. Another thing that we spend a lot of time on is trying to estimate genetic trends. And in those types of models, and you have historical data, it means that you regress the genotypic main effect on release year. And on the other hand, if you also want to take into account that the conditions change, climate change, management, etc., you could regress the year effect on calendar year. And there will be quite a number of contributions on this aspect. Okay, this is something we did a few years ago together with the Australians. I mean, this is attractive in the sense that we try to fit a spatial model for each genotype in relation to the local conditions. So the performance is a function of longitude and latitude, and there are a number of other environmental characterizations that might come into play. And in this way, because these were simulated data, we can show for part of Australia how individual genotypes perform, and we'll try to identify key traits and key adaptations. Okay, so now we get to the core of my talk. Because what we try to do, and what I think we need to try to do, is we need to try to find the right functional forms for describing the G by E. And the right functional forms allow us to insert only parameters that depend purely on the genotype or the environment and not both. And well, if you look at philosophy, then this is called carving nature at its joints. Well, this is what the butcher does, because it's easiest to cut an animal open when you follow the joints. But in plants, it's not so obvious where the joints are, so we need to do a little bit more work. So I think one of the things that may be a little bit underrated or under-evaluated is that if we want to see G by E, well, we need to include the right genetic contrast. If we only have resistant varieties in a trial and we're trying to figure out whether there is, well, G by E with respect to drought resistance, and there are only resistant and tolerant varieties, we're not going to observe anything. So the contrasts that we're interested in need to be present in our genetic material, and in that sense, I favor the use of magic populations, multi-parent populations, because here you have an opportunity to play around with all kinds of contrasts. Same is true for the environment, but of course a lot of work has been done over the last 10, 15 years in managed stress trials, and also trying to find out whether we sample the target population of environments rightly. And I think this is important nowadays. Because of the new phenotyping tools, we can look at the dynamics, and that changes the game, I think, rather drastically. Now, in a sense, Mark inspired me to this. He went to the LIGO Museum, and I think you're never too old to do this. So, LIGO also produces plants nowadays. If the only function of the plant I'm interested in is decoration, LIGO will do. And in a sense, this is the same what we do with statistical modeling. If statistical model provides me with the predictions for the environments I'm interested in, for the genotypes I like, I'm fine. I don't need to go down to the molecular level or the, let's say, finest time scale. Well, this is also, let's say, related to a comment, well, made quite a number of years ago by François Tardieu about these meta-mechanisms. These meta-mechanisms are a way to describe what's going on without going to the molecular details. And, well, a famous meta-mechanism is this thing on leaf elongation in maize, in which the meristem temperature is, well, directly related to leaf growth. And this is a differential equation in which we have three parameters that are all genotype specific. So we can describe how the genotype does by estimating those three parameters. And the good thing of these parameters is, well, here's an example that these are all different circumstances and conditions in which, let's say, for one particular genotype, the relation between meristem temperature and leaf elongation has been measured, and the slope is always the same wherever you are in the world. And here is another genotype that has another slope. Well, this is what we're trying to find out. Cut up the phenotype in such a way that we end up with traits that can be ascribed to individual parameters on genotypes or environments, but not both. We try to do something ourselves. In tomato, this is work by Yutaka Tsutsumi. Eb Heuvelink will talk about it tomorrow. Basically, these are two static decompositions, use a multi-parent population. And after a lot of work, we identified photosynthetic traits, yield components coinciding with yield QTLs. And okay, from there, we need to take it further. It's not, to be honest, immediately obvious that we can improve the existing breeding mechanisms and systems a lot. But surely this gives a lot of insight where the yield QTLs come from. What are the traits underlying the yield QTLs? Okay, the dynamics. This is work that we did together, let's say, with ETH. Well, this is mainly ETH work, but we tried to find statistical models that describe all of these functions in time for different sets of genotypes. This is wheat. These are different subgroups of wheat. that all in their own characteristic way create plant height over time. Okay, these are spline functions. We look at derivatives. These derivatives tell us where important phenological events occur, and we can also look at the value of other traits at those time points. And in the end, what we really want is we want to understand these bumps that we see, whether these can be related directly to something that happens inside the environment, within the trial. And of course, the pretension is that by modeling within trial G by E, we're able to extrapolate to between trial G by E, so we don't have to do all these trials over time and at different locations. If we have the right trial, we try to figure out, by modeling the dynamics, how genotypes will behave in other systems. So we go one step further, because it's also related to a lot of the things that, for example, a company like Hyphen intends to do. If you think of yield, well, yield in a basic form is just resource capture, conversion, and harvest index. There are a number of environmental inputs. So if your phenotyping tools allow you to get a hold on those components and you know what the main environmental drivers are, you can try to fit this in one differential equation system, and then you have a dynamical system that hopefully tells you how the genotype will do in all kinds of conditions. And then if you have the right rate parameters and you can find a kind of molecular genetic basis for those components, for those traits, for those rate parameters, you're fine. So this is one attempt in which we looked at this growth that you just saw in the same platform at ETH, but now we use differential equation that is driven by temperature, and that allows us to have, well, these jumps in the response, which I think is quite promising. Of course, you want to do that also with other environmental drivers. Okay, we initially started with doing this for one trait. We want to do this for a number of traits, for a number of environmental drivers, water, temperature, etc. And we need to do it for all genotypes and all environments in a particular data set. And this, well, what we did is we defined a log logistic model, which is numerically slightly easier to do than a logistic. And each of the parameters in the log logistic is a generalized linear mixed model that once again is a function of genotype and environment. And also, if we want, we can make those parameters a function of G by E. So in this way, in this hierarchical system, estimated in a Bayesian way, if these interactions are about zero, it means that the rate parameters are T and let's say the asymptotes, that they can all be driven by parameters that purely depend on the genotype or the environment. And this would allow us to predict what they do in any kind of condition without further testing. Okay, there is another way of doing it, very similar. This is the whole genome prediction crop growth model. Once again, there is a limited number of yield key components. These are inserted in a crop growth model together with the dynamic weather information, environmental information, and then the whole thing starts turning. And well, what needs to be done is the marker profile needs to obtain the effects that allow to predict the yield components that you identify. And there's another way in which you can try to do it, about which you will hear the coming days. So finally, what it comes down to is that I think you need to use these building blocks of separability, contrast between genotypes and environments, dissection of your phenotype in parts that can easily be modeled in this separable way, and well, look at the dynamics, because the dynamics contain a lot of information that originally we didn't have at our disposal when we were looking at it in a static way. And now I have to check the time, because this, oh yeah, and that is maybe the last thing. We're doing a lot of this now also in combination with other groups, in which we look at combination of mathematics, statistics, AI, etc. Because I think this is a very rewarding field in which there are lots of opportunities to integrate modern computational techniques with classical statistics and mathematics. Okay, thanks. And then I hand over now to Mark, who will take, I think, one question, because otherwise we run out of time immediately.
Thanks, Fred. Even though I inspired you to put a Lego picture on there, you didn't trust me to chair you while you were actually giving the talk. So I'm taking over now. Hi, my name is Mark Cooper. I'm really pleased to be here, and welcome from my perspective also to this community of practice symposium on G by E by M interactions. So what I'll do is I'll allow some quick questions if people have got them. If there's one question that gets too long, that'll be it.
Yeah,
so
exactly.
You can moderate each other. So who's going to put their hand up?
Oh, no one dares now.
Nobody dares. So.
Some time ago, there was a professor in biostatistics in Wageningen who said, we can skip the phenotype, the phenotypic measurements, we can directly go from genotype to yield.
Yeah, this must have been an animal breeder. Well, I was converted. Did I say this?
Yeah.
No, probably was a way to get money.
I think one of the interesting things that I learned at the Lego Museum with the combinatorics that we're actually dealing with, if you take the basic Lego block, the 6-stud Lego block, and you only look at 6 of those, the combinatorics of the different combinations of things you can make with that is just shy of 1 billion combinations. And that's just with one stud with 6 pieces on it. So the whole challenge of dealing with this complexity, if you think that you can explore it without reference to the phenotypes that ultimately farmers deal with, I think you're crazy. Fred, sorry. With all deference to you.
I allow Mark to answer this question. Okay.
Okay.
I
So
think we have to move forward.
Maybe we'll wrap it up there.